Dear students, this is our seventh lecture on stereochemistry and third lecture on asymmetric synthesis. In this lecture, we will see about the different types of methods for asymmetric synthesis, and out of those methods, we will discuss about details of first generation methods. So, the basic concepts of asymmetric synthesis we have already seen. As far as asymmetric synthesis is concerned, basically as defined by Morrison, this is a reaction in which an achiral substrate molecule is converted into a chiral product in such a manner that unequal amounts of stereoisomers they are produced. So we know that if an optically inactive substrate will be converted into a optically active product, generally racemic mixture is formed. Racemic mixture means if 50% of one isomer is formed, 50% of the other isomer will be formed or other anisomer will be. But if one of the stereoisomer is formed in more amount than the other, that is, if unequal amounts of the stereoisomers are produced, then that synthesis will be called as the asymmetric synthesis. So, some of the common functional group transformations which produce asymmetric compound, that is, examples of asymmetric synthesis, they are hydrogenation of carbon-carbon double bond or carbon-oxygen double bond. For example, reduction of these carbonyl compounds to form alcohols. You can see over here, if both these groups they are different, then all these four groups which are attached to this carbon they are different. That means this achiral product, achiral substrate has been converted into a chiral product. And if both the ionomers of this molecule they are formed in unequal amount, then this reduction will be called as asymmetric reduction, or this synthesis will be called as asymmetric synthesis. Similarly, if say same carbonyl compound undergo reagent reaction or Grignard reaction, then also we will produce alcohols, and this achiral reactant will be converted into a chiral product. And again, if both the ionomer formed through this method they are formed in unequal amounts, then this reaction will be an example of asymmetric reaction or asymmetric synthesis. Then if hydroxylation of these alkenes take place, then also you can see two chiral centers they are created over here in an achiral substrate, and this can also be an example of asymmetric synthesis. Then hydroboration oxidation reaction can produce this type of products with chiral centers, or achiral substrate has produced chiral products. Then aldol condensation can also lead to the formation of chiral products, and this can also be an example of asymmetric synthesis. Now, as far as methods for synthesis of these synthesis of asymmetric nature is concerned, there are two types of synthesis which are involved. One is the partial asymmetric synthesis. Partial asymmetric synthesis is where a new chiral center from an achiral center will be uh, formed by using an optically active reagent. Whereas absolute asymmetric synthesis is where synthesis of chiral products or optically active products will be done from an achiral substrate without the use of optically active reagent. So difference between these two is here we will use an optically active reagent, whereas in absolute asymmetric synthesis we will not use any optical active reagent. Now we will discuss first partial asymmetric synthesis. So where we will use optically active reagent either in the form of catalyst or in the form of solvent or in any other form to produce an achiral to produce a chiral center from an achiral center. So there are generally four types of methods which are used in case of partial asymmetric synthesis. First generation methods where we will use chiral substrate. Second generation methods where we will use chiral auxiliaries, that is we will use one part of the substrate attached to some chiral substrate to form an intermediate which will react with another substrate to give us a chiral product. Then we can use chiral reagents which will transfer chirality to the product formation. Our fourth category is where we will use chiral compounds as catalyst, or we can say we will use chiral catalysts. So uh, first method or first generation method where we can use chiral substrate, we know there are many natural products which are present in the form of enantiomers, and these natural products they are called as the chiral pool, and many examples are there. For example, steroids, terpenoids, alkaloids, amino acids. So all these many of these they occur as enantiomers, pure chiral products. For example, nicotine is an example of alkaloid where this is an optically active substrate. So this can be used as a chiral substrate for the production of other chiral molecules. Then camphor in case of terpenes, ephedrine, this is an amino alcohol which can be used as a chiral substrate. Then lactic acid, which is an alpha hydroxy acid, is also an optically active substrate which can be used as a chiral pool. Then pinene, alpha or beta pinenes, they are also chiral compounds. Conene, this is an alkaloid. Ribose, this is a sugar, again a chiral molecule, which can be used for asymmetric synthesis. L-serine, this is an amino acid. This can be used as a chiral substrate. Diglyceraldehyde, L-proline, tartaric acid, all these they are the natural products which we can say part of the chiral pool, which can be used as chiral substrate for synthesis of asymmetric organic compounds, and this comes under first generation. So there are few examples which we will discuss about these chiral substrate being used for the synthesis of asymmetric compounds. So for example, if we are having this anisopure 2,3-butane diol, and this can be easily synthesized from tartaric acid, and this styrophos, uh, this catalyst which is used for asymmetric hydrogenation, this can be synthesized, that means from tartaric acid. So first tartaric acid is converted into this anisopure 2,3-butane diol, and when this is tosylated in presence of toluene sulfonyl chloride, the corresponding tosylate of these hydroxyl groups will be formed, and these tosylate when reacts with triphenyl phosphine in presence of lithium, this will be converted into this gyrophos. So this gyrophos is an asymmetric catalyst which is used for asymmetric hydrogenation reactions. Similarly, this diisopyno camphile borane, this is an optically active catalyst which is used for asymmetric synthesis of secondary alcohols from the corresponding carbonyl compounds through hydroboration oxidation reaction, and this can be synthesized again from chiral substrate of the chiral pool, that is alpha pinene. When alpha pinene is undergoing hydroboration reaction, then addition of borane to this carbon-carbon double bond will take place. Two molecule of alpha pinene, they will give us this optically active organoborane, that is diisopyno camphile borane, which will act as a catalyst for asymmetric synthesis of secondary alcohols. Then first generation methods, the nucleophilic attack on acyclic chiral carbonyl compounds. We have already discussed many examples of this type of asymmetric synthesis, which follow either Cram's rule or Falcon rule, or in the presence of Cram chelation cyclic model, where the metals, they are also involved in addition, nucleophilic addition at the chiral carbonyl compounds, which are acyclic in nature, and the products formed in all these cases, they are optically active products, and the synthesis involved, you can say, is asymmetric synthesis, because one of the enantiomer or diastereomer which is formed in more amounts. Then another example is stereoselective reduction of steroids. For example, if we are having these types of steroids, that is cholesterol 3-one, if this undergoes lithium aluminum hydride, then addition of the hydride to this ketone can take place by these two paths. Either this hydride can attack from the above side or from the below side to give us these two types of hydroxyl products. In one case, where hydroxyl group will be in the equatorial position, and in the other case where this hydroxyl group will be in the axial position. And it has been found that the product formed is exclusively where the alcohol is present in the equatorial position. So this is the major product, because here the hydride ion will attack from the less hindered phase of the molecule. So out of these two diastereomer, one is formed in more amount. So that is why this is an example of stereoselective reduction of steroids. Then conversion of L-tyrosine into L-dopa. So this is L-tyrosine, this is an optically active substrate. So when this is reacted in presence of this enzyme tyrosinase under aerobic conditions in presence of oxygen, then hydroxylation takes place at this carbon, and we will get L-dopa, where optical activity of the substrate is retained in the product, and we can say that a chiral substrate leads to the formation of a chiral product in a stereoselective manner. Similarly, conversion of R lactic acid into S bromopropanic acid through bimolecular nucleophilic substitution reaction. We know that inversion of configuration take place in such type of reactions. Then another example is hydroboration oxidation of isopleugiol. This is a terpenoid. Again, this is an optically active substrate from the chiral pool. When it undergoes hydroboration reaction, then because of the presence of this hydroxyl group, the first intermediate of the borane molecule with this hydroxyl will be formed, which will be converted into this type of addition product. And this borane intermediate after oxidation in presence of hydrogen peroxide and the base will be converted into this diastereomeric alcohol. And the reaction again is a stereoselective reaction. Similarly, the diastereoselectivity in aldol reaction is also example of partial asymmetric synthesis through first generation methods. And these two reactions, all the examples have been already given, that is stereochemistry of enolate, because in case of aldol reactions, the diastereoselectivity is achieved through the formation of either E-enolate or Z-enolate, or depending upon the stability of E or Z-enolate, that product will be formed in more amount. And details of this diastereoselectivity has already been explained in stereoselectivity of enolates as well as asymmetric aldol condensation, which have been already uploaded. So these are the references which are used for preparing this lecture. Thank you very much.